X is a 20-bit chip, which allows for 20-bit pointers. This creates an awkward situation in JTAG because you've got registers that you have to put pointers into, and their length matters. So they did a neat little trick where they kept all of the commands the same length. They just made the extra bytes come last. So when you're shifting in a 20-bit value into the MSP430X, you send the low 16 bits, most significant bit first, then the high 4 bits, most significant bit first. So you've got to shuffle everything as you move it in. There are also 2 line protocols, which only differ in how many pins they use and whether or not they're multiplexed. So JTAG itself uses 4 wires, while SPI-by-wire uses only 2, and it has a sort of meta clock that switches the one data line between the 4 wires of the traditional protocol, even changing its direction when it becomes output from the chip to the host. Inside of JTAG, you have 2 direct registers, an instruction register and a data register. And the data register can change by which instruction register you've chosen. So even though it might seem to make more sense to do things backward by loading the data first and then calling the instruction, as you would in reverse Polish notation, what you're actually doing is choosing where the data goes, and then the action once the data is loaded is based upon the position at which the chip is already at. And this is all a hardware state machine. There should be a lecture on day 4 that'll go into that in more detail. And read that guy's paper in the proceedings. It's worth your time. JTAG itself has these low-level functions. You're either shifting a value for IR, and I say shift because you are writing a new value in at the same time you're reading the old value out. You can't just write and you cannot just read. This isn't very important until you consider that the action happens at the end. So you can never leave the value in the register and hope to grab it later without recommitting the action. Like, if you write an instruction in and then you read it back out, you're just going to cause that action on the other exchange. There shouldn't be 2 DR shifts there. The other thing you might want to do is grab a chip ID. There's a single byte field that can be grabbed for every chip when you send a default command. And this is how you distinguish between drastically different chips. In the case of the MSP430s, even though you've got the 16-bit, 20-bit difference between the MSP430 and the MSP430X, they revamped everything with the MSP430X too. So the commands that you send in order to flash the chip, the way in which flash memory works, they're very different. These are distinguished in that one of them sends 8.9 and the other sends 9.2. In hex. I might have confused those two. But you're identifying the general JTAG protocol by a single byte, and then you figure out what the individual chip is by asking it in that protocol. If you hook a JTAG debugger up to a chip family that it's never been programmed to see, it won't know what to do. There's no specification other than telling it that this is family 5.6 or 4.2 or FE. So aside from the various standards, there's no global standard that lets you read and write everything. To halt the CPU on the MSP430, you load IR data 16-bit into the instruction register. You're choosing which data register you're writing into next. Yes?
It's your time.
What?
Your time.
Oh, you're waving at me. It's a neighborly wave. Fuck you, neighbor. Say it.
Fuck your neighbor.
There we go. All right. So what you're really doing is writing 3FFF into the 16-bit data register. 3FFF is an executable instruction. It's a jump to itself repeatedly. What this does is halt the CPU. It gets it into a state where it won't fail in the middle of an important instruction. And then you put this magic value into the control register, and that actually sets the halt bit to freeze the CPU. And in between, it executes just enough to jump back to itself, so it wakes up at the beginning of the instruction that it intended to next be executing, and it can resume again. Now, all I want you to get from this is that this is really machine specific. 3FFF does not mean jump to self on any chip except for this one, or any chip family except for this one. So lots of things in the protocols won't make sense until you understand the family thoroughly. This does involve reading the family guide and actually writing out machine language on paper, figuring out what the bit fields mean and the opcodes and all of that stuff. This is how you set the program counter. And you're doing something similar. You're just doing a move immediate value into the program counter. to write a flash word, you write the word itself to the address, then you return to read mode, and then you pulse. And this pulsing becomes important because it lets you directly control the flash memory. Have you heard that flash memory has limited life, but that it's really long, so you probably won't hit it unless you use it for flash? Well, that's true, but it doesn't have to be true, and you can control that here. So you're supposed to pulse it 35 times at between 257 and 475 kilohertz. When I was writing this, I thought, it doesn't matter, I'll try anything. I blew up bits. They're now permanently 0. And page erase works similarly, except you're raising them up from 0s to 1s. Flash is 1s by default, and you write it to be 0s. So this creates a bit of an awkward thing in that how fast you talk to the target chip actually determines whether or not the write is successful. If you take the code that works at 3 megahertz and you run it at 12, it doesn't work. And it might even damage the target. Usually in computing, you don't have to worry about damaging anything. You don't have to worry about anything being probabilistic until you get to network optimization and stuff that's really complicated. Here you do. And this is one of the first times I encountered in security that probability theory mattered, and it scared the living hell out of me. So you can burn bits for steganography. You can write a bit more or less thoroughly than you need to. So you can actually store more than 1 bit per bit. Suppose James Bond is crossing a border, and he's got a flash memory stick, and he knows that he's going to get searched. I've only shown this for a 16-bit microcontroller, but let's assume it scales up to gigabytes. What he can do is actually burn in his secret message, force the bits to stay 0 or make them lower than the other zeros, and then he can give up his thing for imaging. And the good data forensics guy who has his proper tools and maintains his chain of evidence is going to make a perfect image of it, recording every 1 and every 0 as it's read then. James Bond then slowly erases it, shaving the chip back up to 1s, and some of the 0s will turn to 1s before others. And that's how he sees his real message. I don't... thank you kindly. So in this day and age, it's a lot easier to just post a torrent file if you want to sneak something across a border, but this is still a neighborly little trick. And you can also use this for exploits. This is where it gets really fun, because there's this concern about, what are they called? Factory supply chain attacks, that's it. So the idea is that an attacker might sell you source material or might mess with your factory in order to change how your product turns out. So if an attacker controls the factory that's programming your smart cards, he could write a virus in there with the smart cards that allows them to give up their key. So you've got your smart card, you think you're secure, you use it for door access, the door just stole your key. You don't know. So what you can do is you can burn an exploit into an unused region of the chip. So at the end of flash memory, you write your little exploit, and then the beginning of flash, where the program begins, that all comes from the compiler. That's all fixed. That's all predictable, so you know which bits to make lower than others in order to change the code to jump into the later time. 10 minutes? Great. So the idea is that you can actually take a chip that you know will be written with firmware built with a particular compiler and nothing else. And you can say, jump into the bootloader if the 5th pin on the 3rd port is high and the 3rd port on the 5th pin is low. And then it will jump into the bootloader when that happens. It might show up as a small reliability issue, but unless anyone is reading the code out, and in a locked chip they might not, and it takes time to verify the code. So often this is skipped during programming. This lets you sneak a rootkit into a chip as it's being manufactured and locked. And once it's locked, you suddenly need a tool like the GoodFET to show that it's been tampered with. You can also do fuse glitching. So on the MSP430, there's a physical fuse that's broken. And it's broken with high voltage. It's physically damaged, at least in the older ones. They changed this in the new generation.